Hello! In this video, we are going to prove the following theorem. E to the 2i arctangent x is equal to 1 plus ix over 1 minus ix for all real numbers x. Now here, context is going to be important. First of all, for us, the exponential function is as follows. The limit of the sequence 1 plus z over n to the power of n is equal to e to the z for all complex numbers z. And from here, we proved many properties of the exponential function, one of which includes the following. E to the z times e to the w is equal to e to the z plus w for all complex numbers z and w. Now, another property we proved regarding the exponential function, which will be important in proving this theorem, is the following. If Zn is a sequence of complex numbers that converges to the complex number z, then the sequence 1 plus Zn over 2 to the n to the power of 2 to the n converges to e to the z. So that's pretty much it for the exponential function. We also defined another function called the arctangent function, and we defined it as follows. Let x be a real number and consider the following sequence. Then it turns out the sequence 2 to the n xn converges. And we define the value it converges to be the arctangent of x. And at this point, this is all we know about the arctangent function. We want to prove e to the 2i arctangent x is equal to 1 plus ix over 1 minus ix. And to prove this, it might be useful to think about how this sequence behaves in the complex numbers. And to figure out how this sequence behaves in the complex numbers, we are going to use the following preliminary result we proved about complex numbers. Let alpha plus beta I be a complex number with magnitude 1, whose real part is not equal to negative 1. Then alpha plus beta I is equal to this. Okay, so now let's get into proving this theorem. To start with the proof, let's first give ourselves an arbitrary real number x. From here, we want to prove e to the 2i arctangent x is equal to 1 plus ix over 1 minus ix. And so to start out, let's consider an arbitrary integer n greater than or equal to 0. Then by definition of this sequence, we know that xn plus 1 is equal to this. And I'm actually going to swap these two guys around. And next, what we're going to do is we're going to divide both the numerator and denominator by square root of 1 plus xn squared. If we do that, we get this. So now, let's apply this preliminary result. We're going to take alpha plus beta I to be the following complex number. We're taking alpha plus beta I to be this complex number. Now, it's pretty easy to see that the magnitude of this complex number is 1. And certainly the real part of this complex number is not equal to negative 1. Therefore, with this choice of alpha plus beta I, this equality holds. Now notice, this is beta, and in the denominator we have 1 plus alpha. So xn plus 1 is equal to beta over 1 plus alpha. So what we're going to do is we are going to replace beta over 1 plus alpha with xn plus 1. And we're going to replace alpha plus beta I with this. So let me just call this preliminary result star. And so by star, we have the following. Right? We get this. But then we can add these two fractions together. We get this. So these two guys are equal. Well then, if we square both sides, we get this, but then if we square this guy, well, we can re-express this as the square of the numerator over the square of the denominator. So we have this, but then we know that 1 plus xn squared is really just 1 plus ixn times 1 minus ixn. And we see that these guys cancel out, and so we're just left with 1 plus ixn over 1 minus ixn. So what do we see here? We see, given any integer n greater than or equal to 0, it follows that these two guys are equal. So this sort of gives us an idea of how this sequence behaves in the complex numbers. So we're going to use this fact to keep going and try to prove this. Now, it's natural to want to apply this result repeatedly. So notice, if we start with 1 plus ix over 1 minus ix, well then, since x is equal to x0, certainly these two guys are equal. But then, applying this result, we have that this guy must be equal to this. But if we apply this result again, then this guy must be equal to this. But if we apply this result again, then this guy must be equal to this. And we could keep going. In general, we can establish by an induction argument the following. We can establish 1 plus ixn over 1 minus ixn to the power of 2 to the n is equal to 1 plus ix over 1 minus ix for all n greater than or equal to 0. So then, if we consider this sequence, well then, every term in this sequence is equal to 1 plus ix over 1 minus ix. So this is just a constant sequence. So certainly, this sequence converges to 1 plus ix over 1 minus ix. But if this sequence converges to 1 plus ix over 1 minus ix, then we should also expect this sequence to converge to e to the 2i arctangent x. To show that, we are going to re-express this guy in a different way. So let's consider an arbitrary integer n greater than or equal to 0. And so now, let's re-express this guy. First of all, we know that this is just the same thing as the numerator to the power of 2 to the n over the denominator to the power of 2 to the n. But then next, we do the following. We have this. All we've really done here was, we multiplied and divided by 2 to the n. Multiplied and divided by 2 to the n. So now, let's think about what the limit of this sequence is. Well, to figure that out, all we gotta do is think about the limit of the sequence in the numerator and the limit of the sequence in the denominator. Starting with the numerator, we know that 2 to the n xn converges to arctangent x. Therefore, I 2 to the n xn converges to I times arctangent x. And so because of this, it follows by the first fact that we have here, that the sequence in the numerator converges to e to the I arctangent x. And next, as for the sequence in the denominator, we know that negative I 2 to the n xn converges to negative I arctangent x. And so because of this, it follows by this fact that the sequence in the denominator must converge to e to the negative I arctangent x. And certainly, e to the negative I arctangent x is not equal to 0, right? E to the power of any complex number is not equal to 0, because if you do e to the z times e to the negative z, well, that has to be equal to 1. So there's no way that e to the z could be equal to 0. Right? That's the reason why e to the negative I arctangent x is non-zero. Right? And we need that to be true, because now that we know the limit of the sequence in the numerator and the limit of the sequence in the denominator, which is non-zero, we can use the division rule for limits. Right? It follows that the limit of this sequence must be e to the I arctangent x over e to the negative I arctangent x. But then we know from properties of the exponential function that this is just e to the 2i arctangent x. And then we know that the limit of this sequence is precisely the limit of this sequence. Right? Because we showed that these two sequences are exactly the same sequences, right? We showed given any integer n greater than or equal 0, these two chi's are equal. That's why they converge to the same value. But we showed earlier that this sequence converges to 1 plus ix over 1 minus ix. So we see that e to the 2i arctangent x is equal to 1 plus ix over 1 minus ix. So this completes the proof. And so yeah, that's pretty much it for this video.